So up until this point, what we've been saying is that these are the things that affect the amount or the rate of heating. So we've said, number one, the angle of insolation affects how quickly areas will heat. So areas like the equator, there's going to be direct sunlight. And that direct sunlight is going to be more concentrated. It's going to make it hotter near the equator. Near the poles, where that sunlight is coming in at a very low angle, it's very indirect. The sunlight is very dilute. It's very spread out. It's going to be colder. Also, there's duration. Now, duration, I'm sure you know this, but the duration means amount of time. So the longer the sun is in the sky, the more opportunity it has to heat an area, and therefore the hotter it's going to be. So in the summer, not only do we have sunlight that's higher in the sky, we have really long days. The sun comes up at like 5:30 and doesn't go down till 9 o'clock. Therefore, it's really, really hot during those times. And in the winter time, the sun doesn't come up till after 7. It goes down at like 5 o'clock, and it's low in the sky. Those two things come together and give us pretty cold days. So that's where we've been so far. So far we've said the reason why we have weather is because the sun heats up different parts of the earth unevenly because of angle and duration. But that's not the whole story. There's a whole lot more to it. And we're going to talk a little bit more about that today. And we got to remember this stuff for the future. Now, number two, the second factor that affects the amount or the rate of heating is land versus water. Now, I'm sure you can relate to this. It's summertime, it's late July, it's the afternoon, you want to go to the beach, so you drive to the beach, you get out of the car, you're walking down towards the sand, you kick off your flip-flops, you step in the sand, and it's like stepping on the surface of the sun. It's so crazy hot. It is for me anyway. It's really, really hot, and so I tiptoe as fast as I can all the way down to the water, and I put my feet in the water, and it's totally cold. You guys relate what I'm talking about? So what's the deal? So it's the same sun shining on the sand and the water. It's the same angle on the sand and the water. It's been shining on the sand and the water for exactly the same amount of time. So why the big difference in temperature? Well, I want to talk to you just for a minute about something known as specific heat. And this is just an introduction to specific heat. But essentially, what's going on here is that all objects have something known as specific heat. So all these numbers are in joules per gram times degrees Celsius. Don't concern yourself with these units. Don't concern yourself with these units. You're not going to have to really do anything with them. But here's what I want you to understand. Liquid water, like the ocean, like the beach water, is 4.18. Now, sand is just little bits of rock, remember? So it's little bits of basalt and granite and maybe some iron and copper and lead. But look how low those numbers are. So really small compared to liquid water. So sand heats up faster and it's got a low specific heat. Water heats up slowly and has a high specific heat. So get those numbers. Think about that. High number takes really fast. Now here's the other thing that's true. What's going on at nighttime at the beach? Anybody ever go swimming at night? It's awesome. It's awesome. The first thing that happens is that the land cools down. The sand, when the sun goes down, the sand is just cool, wicked cold. You go in the water, it's awesome. It's warm. Because that water has been heating up all day long. Things that heat up quickly, cool off quickly. So specific heat means that these things heat up quickly and they cool off quickly. This high number means that water takes a long time to heat up. It also takes a long time to cool down. It holds on to that heat and slowly gives it off until the sun comes up and it starts all over again. So that's what's going on here. Right? So the land heats up quickly, cools down quickly. The water heats up slowly, cools down slowly. This is why some of us heat our homes with hot water, like heat our rooms with hot water, because that water, it holds on to the heat for a long time, slowly gives it off, and keeps the room warm that way. The downside of that is it takes a lot of energy to heat up that water. But whatever you put into it, you're going to get out of it. So here's the deal. Land versus water. Land heats up and cools down faster than water. Now here's what we're going to learn later. Because of this, if you live near a really large body of water, if you live near the ocean, or if you live near a Great Lake, that's really going to have an effect on your weather. So, for example, if you live near the ocean, even in the north, even in the winter near the ocean, you're not going to get a lot of snow, because all summer long the ocean has been heating up, and all winter long it gives off that heat. And so these coastal cities are not going to get super low temperatures, because the ocean is going to warm the land all winter long. Us, where we live, we don't live near a very large body of water. Of course, we have the St. Lawrence River, but that's not big enough. This is why we get really, really cold temperatures in the winter, because we don't have a large body of water to help moderate those temperatures. So more about that later. All you need to know right now is this. Okay, number 3, the third factor that affects the amount or the rate of heating is color. We have dark color versus light color. Now here's what's going on with color, right? Light, sunlight, incandescent lights, they're white light. And in that white light, there's all of the colors. Red, orange, yellow, green, blue, and violet. They're all in there. Together, they form white light. Now, this right here is white because all of that white light is bouncing off it into your eye and my eyes. All of the colors. This one right here, none of the colors are being reflected. All of them are being absorbed. None are being reflected. Wissa's sweatshirt is red, right? The white light is hitting that red. His shirt is absorbing orange and yellow and blue and green. Do you guys see any of those colors on him? No, because his sweatshirt is absorbing all of them, but he's reflecting the color red. I got a lot of red on here today. Okay, so if you're wearing a blue shirt, then you're absorbing red, orange, yellow, green, and violet, but you're reflecting blue. You're absorbing some colors, you're reflecting other colors. This is reflecting all the colors. This is reflecting none of the colors. Now, if you're reflecting all the colors, then you're not really absorbing anything. If you're absorbing all the colors, you're not really reflecting anything. What happens when objects absorb light? What does it turn it into? Heat. This is why in the summer, if you wear a dark colored shirt, you're going to feel warmer than if you're wearing a light colored shirt. This is why snow doesn't just melt even though the sun is up for a long period of time, because it doesn't absorb much, it just reflects it. So here's the deal. Dark colored objects heat up faster than light-colored ones. Please forgive my handwriting today. Okay, so quick recap. So things that affect the rate of heating on Earth. Angle and duration of insolation. Insolation stands for incoming solar radiation. Land versus water, they heat up differently. Dark-colored objects heat up faster than light-colored objects. Next, texture. texture. We have smooth textures and we have rough textures. Now a smooth texture is going to just reflect. Stuff is just going to bounce right off it. Rough textures, those aren't going to bounce off. They're going to get more diffused. So more likely that light is going to be absorbed and turned into heat here. So rough surfaces heat up faster than smooth surfaces. Rough surfaces heat up faster than smooth surfaces. Now usually in the Regents questions, these two are usually grouped together, and the questions kind of go more like this. Pay attention. So what is going to heat up faster? A forest or a snowy field? A forest will, because forests are darker and they're rough textured, whereas a snowy field is going to be very light in colored and very smooth. So there we're going to take that information and then apply it to our real world situation. Okay. Let's turn to our next page, page 10. So mapping a temperature field. So here, once again, here's that word isotherms. Isotherms. Most of you didn't know the answer today. You should know it for tomorrow. Isotherms are lines that connect points of equal temperature. Isotherm, equal temperature. Showing temperature distribution in this way makes patterns easier to see. So what we're going to do is we're going to draw isotherms at 10-degree intervals for the 30, 40, 50, 60, 70, and 80. And I'm just going to do it, and you're going to follow my lead. So here's what's going to happen. We'll do the 30 first. We're going to start in Calgary. And I'm going to start drawing my line. We're going to go through Calgary. We're going to go through Bismarck. We're going to cut through Winnipeg and Minneapolis because 30 degrees is almost halfway between 27 and 34. We got to go up above Sault Ste. Marie, and then we'll go out through Father Point. So everything above this line is less than 30 degrees. Everything below the line is greater than 30 degrees. We've just drawn our 30-degree isotherm. Bless you, bless you, bless you again. Number 4. I'm sorry, 40 degrees. We're going to go through Seattle. We're going to go through Butte, Montana. We're going to go through this one that has no name on it. We're going to come down in between Minneapolis and this 46, just about halfway. We're going to go through Chicago, over the top of Detroit, through Buffalo, and then out between Boston and New York. So now, what I've done here is, when I drew this line, I divided up my entire map into those that are less than 40 and those are greater than 40. I'm just going to list, I'm going to write down what my isotherms are. Now the 50. We're going to go through this 50. We're going to go below, what does that say? Balsa?
Boise.
Oh yeah, Boise, Idaho. We're going to go down below Boise. We're going to above Salt Lake City at 57, close to Denver, right into Kansas City. We go halfway between Chicago and Cincinnati. And then I have to now come down between this 45 and the 60. Down through here near Richmond, and then out to the ocean between Richmond and Hatteras. So that is our 50-degree line. A few more. Let's do 60. 60 goes through San Francisco. And then I got to go down between Phoenix and Roswell. Closer to Roswell, that's where all the aliens are. That's where the aliens crashed. Did you guys know that? and then down to Galveston, Texas, and then 56 and 70 up through Little Rock and Chattanooga up to Cincinnati, and then I got to squeeze out right through here because 60 is between 50 and 68. That one is 60 degrees. Stop making unnecessary noises, please. Two more. 70. 70 is going to ride between Galveston and New Orleans. There's a 70 right there. I'm going to go right to that. And then I'm going to come out just north of Charleston. So everything down here is greater than 70. And then my 80 is just going to do that, right? That's all I need to do. Now once I've done that, now I can see sort of a general, I can see a temperature distribution pattern. I can see that. I'm also can kind of see air pressure, which we'll look at later. Now that I have this, we'll talk about temperature gradient. Gradient, if you remember, gradient is just like slope. It's no different than slope that you do in math class. And so gradient is, temperature gradient is the change in temperature over a particular distance. And the greatest temperature gradient, where is that happening the most, is right in here. So that's between Richmond and HA, Hatteras. And the reason why I know that is because the isotherms are closest together. The isotherms are closest together. Just like the steepest slopes are where the isotherms are closest together. The greatest temperature gradient is where they're closest together. The greatest air pressure gradient is where they're closest together. Where are they farthest apart? Over here. Why? Because the isotherms are farthest apart. So the last thing I want to talk to you about is calculating temperature gradient. Temperature gradient, what is the temperature gradient between Cincinnati and Chicago? And tomorrow on your quiz, I'm going to ask you the same thing. So, the first thing we need is our formula. Right on page 1 of your reference tables is that formula. There's the gradient formula, and this can be used in for multiple field values. So the gradient is the change in field value divided by distance. We're going to do the temperature gradient is the distance between temperature divided by distance. So the first thing I do is I write down my formula. Because if I write down my formula, it's very unlikely that I'm going to make a mistake. So temperature gradient is the change in temperature divided by distance. We always do it the same way. Now, from Cincinnati to Chicago, the change in temperature from Cincinnati to Chicago. There is Chicago. It's 40 degrees Fahrenheit. Cincinnati is 60 degrees Fahrenheit. So that's a change of 20 degrees Fahrenheit. Change in temperature, 20 degrees Fahrenheit. Divided by the distance. Now to find the distance, I'm going to take some scrap paper. I'm going to lay it down right there. I'm going to make a mark at Chicago. And I'm going to make a mark at Cincinnati. So there's the distance between my two cities. Then, all good maps are going to have a scale. I'll take this down here. I'll put it on my scale. And there's 0. That's 200. And that's 400. That must be 300. So that's 250. 250 miles. So for distance, 250 miles. Then I go to my trusty calculator, and I know that I'm dividing a small number from a really big number, so I'm gonna get a fairly small number. It's a good idea for you to do like a little bit of guessing, estimating before you start. So 20 degrees Fahrenheit divided by 250 miles gives me a pretty small number, 0.08. Now, in terms of my units, I took degrees Fahrenheit and I divided them by miles. So my answer is going to be degrees Fahrenheit per mile. And that's how you do temperature gradient. And the one you do tomorrow, same idea, no tricks. Tomorrow, please study pages 9 and 10. Know all about factors that affect the heating of the earth. Know about isotherms and calculating gradient.